n equal 1, its behavior is quite different, close to the cutoff. But as we increase the total number of modes, it will become accurate again. So modal effect does plays a very important role. I've shown you. This is a potential whale case. How about potential barrier case? Okay, it's the same. This is transmission. As we increase the mode, the accuracy will be increased. At mode up to 9, it agrees with the simulations very well. Very well. But potential whale, we need 21 mode. However, potential barrier, we need 9 mode. What happened here? That's because wave cannot propagate inside. So we don't need too much mode here because most of the wave are adolescent wave. Adolescent wave. Adolescent wave, in that case, we don't have to calculate too much more. Okay, that makes sense to us. Look at the group delay. Group delay versus the frequency. As we increase the total number of modes from 1, 3, 9, it agrees very well, very well. Look at the green, red line here. So in these regions, the nominal speed, nominal delay will be 0.5 nanometer. So in these regions, it is faster than the speed of light. In these regions, wave cannot propagate. A wave can propagate, cannot propagate. But its group delay is faster than the speed of light. Group delay. We don't like group velocity faster than the speed of light because it's, I don't know, I just don't like group velocity faster than the speed of light. We prefer group delay here. Okay, this is the third summary. We just demonstrate the modal effect plays an important role for a three-dimensional discontinuities. And so I will show you, I will simplify the equation a lot later because we have to consider too much more. It's not easy, it's too complicated. And to achieve a better agreement between the theory and experiment in quantum tunneling, the modal effect should be considered. What does this mean? This means in most of the quantum tunneling system, they use one-dimensional because of calculation. It's not that easy. Here, I just show you three-dimensional waveguide. We have to consider discontinuity problems. We have to consider all the possible modes inside. So in the quantum system, maybe we should consider three-dimensional effect. We should consider more modes. Then the result, the experimental result and theory will agree much better. This is our suggestion. Okay, now let's move on to a more important topics. Up to this point, we observed, we have shown you the supernominal effect. Faster than light effect can occur. But the problem is they are evanescent wave, not propagating wave inside. So transmission is low, very, very low, roughly about 0.1%. So transmission is low. And as I just showed you, close to anomalous dispersion, bandwidth is very, very narrow. Transmission is low, bandwidth is also very narrow. It's not good, and just, I can say that, useless. Just interest in theory only. Okay, so we are going to propose a new mechanism. This mechanism allows us to have, this mechanism has broader bandwidth, much broader bandwidth, and much higher transmission compared with the previous two mechanisms. previous case, the waveguide width is narrow. However, in this case, waveguide height is changed. So wave can propagate in this waveguide, can also propagate in these regions. But what happened here? There is a discontinuity here. We will excite high order waveguide mode, as I just mentioned. But this waveguide mode, in addition to the fundamental mode, high order waveguide mode are evanescent wave. There will be exponential decay. Exponential decay, exponential decay. So high order waveguide mode will modulate the amplitude and transmission, the amplitude and the phase of transmission and reflection. So by doing so, we can simplify the problem into quasi one-dimensional. We just reduce the three-dimensional problem into one-dimensional. And other high-order modes comes to here. We have extra phase, extra phase, extra phase, and transmission, reflection will be slightly changed, slightly. Well, this will play a very important role because in quantum system, in optical system, they omit this effect. But in microwave system, we have to consider this effect because this will play a very, very important role later. We are going to manipulate this part, the phase turns. Okay, look at the magnitude. This is the first part, first boundary, R, and second boundary, region 1, 2, 2, 3. Okay, agrees very well. And the phase, here is the phase. Phase is here, this one, and another one. This is reflected phase, from inside to outside, reflected. Okay, so this is reflect. This is transmitted from here to here. So we have extra phase, extra phase. And this one associated with this boundary because we have two boundaries in this case. So luckily, the existence of higher order modes, which are evanescent wave, will modulate the amplitude and the phase of the dominating modes. So we can reduce a three-dimensional multi-mode problem into one waveguide mode. Simplify the problem a lot. Okay, how to do the experiment? This is the schematic of our experimental setup. Incident wave here, and transmitted here. This region, cut off, they are all the same, which means wave can propagate inside. Inside the region of interest, wave can propagate. But here, this is a time domain problem. We have to generate a wave packet. How to generate a wave packet? Here we use these techniques. Signal generator give us a sinusoidal wave, sine wave, beautiful sine wave. And then we use a pulse generator together with a pin switch. Pulse generator give us this one. And pin switch, on and off. This give us we can construct a wave packet like this one. Then the wave packet is introduced into a power divider, divided into two parts. One is reference. The other is go to the device under test. This one looks like a waveguide adapter. Waveguide adapter here. And this is a device under test, which is this section. Okay? So by comparing the difference, we can calculate the group delay. Okay. So we must keep these two, the red line and blue line, equal lengths. Otherwise, we'll have some trouble. So we have double check the result. Also, we can measure everything in the scope. This is the information we can measure. we can generate using a pulse generator, and we can using a simple approach that is two-way mixing. Frequency F1 together with frequency F2 generate a bit wave, two waves, and we can measure the group delay here. The same, quite similar. Okay, this is experimental result. This is a luminous speed. That is because the length is 10 centimeter, so it's about group delay should be 0.33 nanoseconds. Above this one is a slow wave, which means wave propagate much slower than the speed of light. And below this line is a phase wave. As you can see here, the behavior is quite agrees very well. Time domain simulation and experiment agrees very. I think it's okay. Agrees okay. Okay, let's focus here. This is a resonance transmission. It's a slow wave structure. Slow wave. As you can see here, this is amplitude, and this one transmitted amplitude. This one corresponds to input wave. This is transmitted wave. Input transmitted. Resonance transmission. So they are equal amplitude. But group delay delays a lot. If we can properly design the structure, the group delay will become very, very sharp. The energy is stored inside. So the group will, the speed will become much, much slower. Much, much slower. This is the mechanism of slow wave. Look at this case here, for example. Incident wave is black dashed line, and transmitted wave is red line. They are almost overlapped with each other. And you can measure the group delay just a little bit compared with this one. 330 picosecond, but here just 63 picosecond. So the group velocity is clearly faster than light. And in this case, the group velocity is equivalent to 5 times the speed of light. But look at the transmission. This is a 1, 0. But transmission is much lower. It's not evanescent wave. It's propagating wave. But transmission is not 100%. Of course, if it is 100%, then Einstein will become very unhappy. So transmission just a little. But this one is large enough compared with other mechanisms. Okay, look at this case. This is the relation between normalized high, this one, the high, we can normalize this one, versus apparent, looks like group velocity. So we'll give it another name. Look apparent group velocity. Okay. Transmission, when the high is the same as B in this case, it is 100% transmission. Obviously, 100% transmission. And group velocity will be lower than 1. Okay, reasonable. However, as we change the height of the waveguide, then the group velocity will be increased, but transmission will be decreased. Okay. We are operating close to these regions. 1, so the group velocity is about 4, roughly. 4 times the speed of light, 4 to 5 times the speed of light. So we can change the group velocity by changing the waveguide height, here in this case. So this might stimulate theoretical interest. What is the theoretical limit for superluminal effect? What is the 47% in this case? What is the theoretical limit? 50%, 60%, or 50%? We don't know. Up to this point, we have no idea. Okay. This is another case. Okay, as you can see here, this is transmission. The inset is transmission. Transmission is shown here, 3.2%, which is the highest for the superluminal mechanism. We have highest transmission. 3.2%. It's still too low, but at least it's good enough. And this is frequency. Frequency, and this is group delay. As you can see here, the length 10 centimeter, quite broadband, 30 centimeter, group delay here. 50 centimeter, 70 centimeter, 90 centimeter, group delay is linearly proportional to the length, which means wave can propagate inside. It's a strong evidence that wave can propagate inside. So this is the fourth summary. This is a new mechanism of the superluminal effect. We have theoretically analyzed and experimental demonstrated. In contrast to the traditional mechanism, which involve evanescent wave, this mechanism employs a propagating wave. We have a high transmission and broad bandwidth. So what's next? Next one is to manipulate group delay, to control the group delay.
Well,
Okay.
So in terms of a total Poynting flux, it really doesn't exceed the speed of light.
Yes.
Because you have reflection.
Yeah, most of the wave is reflected back.
Okay, and but you can kick out sort of wave packet that is faster than the speed of light.
Only a small fraction of the wave packet is faster than the speed of light. Only a small fraction. In this case, 3%.
Oh, I see. Okay.
But they should maintain the same shape. The shape should not distort. The shape will be the same. But only a small fraction will faster than light. Okay. Next one. We know the phase here at the discontinuity plays a very important role. So can we control this phase, this one? Can we control the phase? Yes, we can do that. Here, we use the waveguide is the same size. This structure looks like a fabric pillow structure. Two mirrors, and wave can partially transmitted and partially reflected, mostly reflected. And wave will bounce back and forth inside. Our job is to control the phase here and phase here. Two phases, this phase and this phase. This phase and here. So wave is propagating inside. So this is a simple model, as I just showed you. This is amplitude, transmitted amplitude. This one corresponds to phase, and this is transmitted amplitude. In this case, about the same. About transmitted amplitude is about the same. As you can see here, this is simulation result, multi-mode theory. That is, we reduce multi-mode into one. Our theory and experimental result agrees very well. So this gives us confidence. We can manipulate the phase here. We can change the size of the iris, just like a camera shutter or throttle. You can change the size, then you can control the group delay. Okay. So up to this point, group delay very close to 0, but it's positive. Can we control the group delay? So the group delay will become negative. Before that, let's have a look at this one, a complete definition. So how to calculate a group delay in this case? This is a transmission and reflection at the first boundary and at second boundary. This is a final group delay. This one associated with, this is a traditional definition. Length divided by group velocity in the middle region. So this is a previous understanding. However, wave will bounce back and forth in between. So they have a multiple reflection factor here. They will place a row, boing, boing, 2 times. So 2 times here. So this will place a very important role here. Next one is here. This is due to the phase. This is the discontinuity in the boundary. In principle, it will spend no times, but sorry, it will. So we have a first boundary, second boundary, so 2 times. And doing 2 times the multiple reflection factor. And last one is shown here. So this one is traditional understanding of the tunneling effect, of the traditional understanding of the propagating wave. And this one is dispersion behavior. If it has some anomalous phenomena, it will be here. So this equation comprises almost everything. This one is new. This one is new. No one mentioned this equation before, because in most of the systems, they don't have to worry too much about the high order mode. However, in our case, high order mode will modulate the phase. So this is a new term. We are going to use this one to control the group delay and let the group delay become negative. Okay, so this is the definition here. Dwell time, traditional understanding, boundary transmission time here, boundary reflection time here, and dispersive time, anomalous dispersion, if occur, will be here. Okay, let's consider 2 criteria, 2 cases. One is phase wave, the other is slow wave. What is the difference? When it's a slow wave, which means it's a constructive interference. It's a resonance cavity effect in between. So it's an unresonance. So R prime will be very close to 1, for example, 0.9. Then this term will become very large. This term will become very, very large. Compared with this one, that's not important at all. And this one is also will become large. So the group delay will become very, very large. That means the incident wave will bounce back and forth. The EM wave will be built up inside. So this is why resonance interference will result in slow wave. On the other hand, this is destructive interference. So it's destructive, not constructive. R is very close to 1, so this term will be small. And this term will be positive. However, we are lucky. We can control the phase. So by controlling the phase, this term, the phase term, will become negative. We have a chance to let this term become negative. So how to do that? The answer is quite simple, yes. We are going to implement the idea in a bifringing waveguide system. This is our waveguide system. Okay. So it's a cross-sectional view is here. We have 4 slabs. 4 slabs divided into 2 orthogonal, 2 axes. So wave, for example, here can be divided into 2 parts, equal amplitude part. if this angle is 45 degrees, okay, 45 degrees, and the slot is slightly different. One is LX, the other is LY, which means the wave can propagate inside, but their propagation constant will be slightly different, So this is the ordinary mode, extraordinary mode here. Just two orthogonal modes. And by control the incident wave and the phase effect, here is the experimental result. This is a normalized amplitude. Red line is simulation result. This one is we consider bifringing crystal, bifringing structure, and this is experimental result. Solid dot. Okay, so solid dot is here. That agrees. Okay, not exactly the same, slightly different, but at least the behavior is quite similar. The difference might be machining error, okay, because the frequency is quite high. The frequency is quite high here. And this one is transmission and phase. So the phase with respect with the frequency is the group delay. So in this region, the group delay will become negative. Negative here. Group delay become negative. This is 0. This is the profile, the time domain profile of the incident wave and the transmitted wave, transmitted pulse. So the incident is a dashed line, black dashed line, and transmitted is smaller. Transmitted is here, incident is here. And it looks like the same height, but in fact it's not. Only a small fraction of the wave can be transmitted back, but about 3% in this case, about 3%. So most of the wave is reflected back, as Professor Chen mentioned. Most of the wave is not transmitted. Only a small fraction is transmitted, but the group delay is negative. It's quite strange, but the group delay is negative. Okay. This is only for Gaussian wave only.
This is a measurement.
Yes.
Oh,
this one is
no.
No, this one is not. This one is from this one to Fourier transform.
Linear combination.
Yeah. Okay. Inverse Fourier transform.
Because the top two panel seems to be a single mode analysis, and then you cross the frequency, right?
Mm-hmm.
Has to be.
Yeah.
So you just do the Fourier combination to obtain that.
Yeah.
But do you have a measurement?
We have in this case no time domain measurement because we have confidence the frequency domain and time domain are closely related. So we have confidence. Yes, in this case we don't need to perform the time domain. The major difficulty is to generate a time domain web packet. It's not that easy.
So you use a post generate.
Yeah, but only a few cycles here, or maybe just 2 or 3. Not high enough. So in this case, we have to use a different approach. At lower frequency, yes, we can modulate.
Okay.
But at higher frequency, sorry. Okay. So this is the last experimental result. We can change the group delay by changing the angle of the incident wave. If the incident wave is here, that's 45 degrees. So for example here. If incident angle, we can rotate the waveguide a little bit. If the wave can rotate here, this is another group delay. They are all negative, but the behavior is different. So if the carrier frequency is 32.5, then, as you can see here, by changing the angle of the incident wave, the group delay